I'm Shimon Ben-David, the Chief Technology Officer for WEKA. What I wanted to do is actually to start with AI. So let's talk a bit about AI first, how AI workloads looks like, and then definitely how they relate to storage environments, or how do they relate to storage IOs, and what do we see customers experiencing. And as we heard from David and Colin, we actually have a long experience with AI customers going back from the early days of the company, where actually the hardware wasn't even ready for these massive AI projects. And now today, we see some of the largest AI projects on the planet actually running on WEKA. Let's talk a bit about AI environments. And again, we'll start talking about AI, and then we'll move to the storage side and how WEKA facilitates that, and what's our unfair advantage even, I would say. So if we're looking at the AI challenges, we see that there's obviously all of these accelerators. NVIDIA is owning a large percentage of the market. As we mentioned, they broke Moore's law. You have thousands of cores running computations in parallel. You also have a lot of the newer ones, Cerebras, GraphCore, Sambanova, TensorStorrent. We actually work with a lot of them on some joint projects, so and validation. So there's a lot of advance in compute. So compute moved a lot. Also, I think since in the last few years, we saw that there's a lot of advance in MLOps environments. So orchestrating environments, running distributed AI workloads, Kubernetes clusters running under the hood, because eventually in modern AI, everything is containerized. So there's a lot of advancement in that. And now we're asking ourselves, what about the storage and data platforms for AI? Are they relevant? Do they need to adapt to AI? Yes, no, is what we have today and what we had yesterday, maybe that's sufficient, right? So I wanted to go over a few, over that pipeline that Colin mentioned, and we'll go on a few steps within the AI pipeline and talk about the challenge, and obviously how it relates to a data platform and to a storage environment. So first of all, let's take a look at the ingest. All of the data pipeline begins with ingest because AI requires massive amounts of data. Starting, by the way, small AI environments are starting with double-digit terabytes. So hey, that's not even that big. But as they mature at day 2, day 3, day 4 operation, you grow in the amount of compute resources that you need, and also in the amount of data. And there's obviously this notion of data as code. If I can feed a model large amounts of data, obviously it will be better than a model with less amount of data. So I need to ingest a lot of data into my environment. The data usually comes, again, in mature environments worldwide. So now you need to accumulate data from a lot of sensors in edge locations, autonomous cars, recordings, and now you need to mobilize that data to an environment. Maybe there's some edge training, but mostly inference is done at the edge, but training is done at some core. So you need to mobilize the data from multiple geos to a centralized environment, and that's by itself is a complicated task, because if I'm gathering terabytes per hour, and now I need to centralize that, how do I mobilize that data to a centralized location? Rules, regulations, and just the practicality of moving that data around. When I move that data around to the ingest, I also want to enrich it. I want to sometimes tag it, label it, right? So that's another thing that the ingest part can think about it as being that it needs to handle. So that's already a challenge by itself. Next, we're moving to the what we call here the ETL, the pre-processing. So the pre-processing is actually, I think we can call it the best known secret in AI, right? So, and that's like, let's take a second can take 50% of a training epoch's time. And by the way, that's generous, it can take even more. So the pre-processing is actually the stage where we manipulate the data, where the data scientist needs to manipulate the data, so then their AI model can accommodate for it. So for example, if I'm now working over images, I need to resize images. Every model or every data scientist, I would say, is expecting their images to be in a specific size with a different color correction, contrast. So every data scientist is now pre-processing their data in a different way, and that's massive. That's the period of time where the data didn't even reach the GPUs. So we'll constantly talk about GPU workloads and accelerator workloads, and that's baffling because a lot of the AI workload, a lot of the training job time is actually even before it reaches the GPUs. So, and what we see therein is that, as I mentioned, within an organization, there are huge variations. So you see multiple organizations are pre-processing the data in a different way. And it's even more complicated than that, even within a single organization, data is being manipulated in a different way. So could be that I have multiple raw images, and where you ask about copying the data and multiplying the data, could be that I have multiple raw images or raw data, and now I have 10 data scientists, and each of them will pre-process the data in their own effective way that would correlate to how they're expecting to see it. That actually, we already covered that. The I/O implications, because we do want to tie it to the storage eventually, or to the data platform, the I/O implications are actually are massive. So there's massive amounts of reads, there are massive amounts of writes to the data and to the data platform. And by definition, it's a write cache miss because you need to write the data to the stable storage. You need to read massive amounts of data and then write them back pre-processed to the stable storage. Again,
when you see most of the AI activity happening in organizations today, or happen in like groups or silos, so that one group is working on a specific model for a specific application, another group would be maybe using the same data for another model for a different aspect of that. And
yeah, it's usually about
don't
business.
Talk together or work.
No, I would say that we do see collaboration. Different organizations work differently. Usually there is collaborations. Usually you will see different groups working on the same data for a different outcome. So it all relates to how many AI projects does an organization have.
The pre-processing for each of those outcomes would necessarily be different.
Exactly. And that's huge. That's even before you get to the GPU, you have a massive I/O workloads, reads, writes, variations on the compute for that data.
Does something like a feature store fit into this framework?
A feature store eventually relates to the training part, because when you train the data, you want to connect to your feature store and understand what you're trying to look at it. It's still not in this stage.
Some step after pre-processing.
Exactly. It's actually more in the training part. So we talked about pre-processing. Now, I want to show a few examples. Again, very simplified example, but I think they'll drive the message of how an I/O pattern, or what does a training model steps, how would they look like? We'll start with a small data set. We'll go into a larger data set. And how does it look like? Because I think there's these notions where, hey, sometimes our current storage is enough. Our yesterday's storage is enough. Why do we need to improve on it? So let's take a look at a small data set. And as you know, GPU servers, multiple GPUs, each GPU has a certain footprint of HBM, high bandwidth memory within it. So how does a training model of a small data set looks like? And let's focus on a single GPU server. So obviously, we'll start with the pre-processing. So I'll now read my data into the server memory, into the RAM of the server, not even the GPU. I'll read the data. I'll perform my pre-processing. I'll cut the images. I'll change the contrast. I'll change the pixels as needed. Again, for computer vision, for example. And I'll write it back to stable storage. That already took some time. Then I'll read again the pre-processed data that because I went over my data sets, and I'll reread it again. And now I'll also read it, after it's in my memory, I'll also read it into the GPU memory. So now I'm loading the data into my GPU memory. And because it's a small data set, in this example, the data fits into the GPU memories, right? Now I can train on the data. I'm running my model on the data. The data is in my GPU memory. Everything is okay. Maybe I have some outputs I'm saving, and then I'm repeating that, because I'm getting some of my hyperparameters will also say how many epochs and what's the accuracy that I need to extract from my data, right? So I'll just repeat this process. And again, the data is in. Maybe I'll also shuffle the data in memory, so I don't always read it at the same time. So it's a bit truer. So my model wouldn't expect the same data all the time. But again, it's in my memory. What's the benefit? What's the disadvantages? So hey, small data sets can fit into GPU memory. So they're effectively almost eliminating storage latency, because if now I loaded everything to my memory, the storage is less relevant, right? But as we saw, small data sets, pre-processing will still require reading and writing the data. So I can't get away from the pre-processing that needs to be done. And that's a storage workload. And even if my data is in memory, in many cases, I still need to do metadata operation, shuffling through files, getting attributes. They're not all cached. So Ray, I think to your question before about constantly copying massive amounts of data, the copy is not always intentional. So sometimes the copy is being done where I have Maybe I have a centralized NAS environment, and now I'm working on that data, and the copy is actually caching the data on the local NVMEs of the GPU servers. Sometimes it's just really copying it directly, but sometimes it's being cached as a result. So in a small data set, I would say there's still storage significance, but some is eliminated. On a larger data set, so hey, now my AI practice grew a bit. I need more to go over more data. Maybe maybe my one GPU server, but now basically everything looks the same, right? Same steps as before. I need to read my data. I need to pre-process it. I need to read it into the RAM. I load it into the GPU, but now I don't have enough memory in my GPUs because it's a larger data set, right? I need to train on the data. So what we're seeing customers doing is actually using the double buffer mechanism where you take a look at the GPU memory. Obviously, that contains your model, your parameters, and you take what remains out of it, kind of like you split it to two, and then you're loading data to half of it, and you're training on that half while you're loading more data while the training goes on. So you're effectively trying to create a buffer where you eliminate the storage because you eliminate the reading from the storage because you're training on a small subset of the data. So there's that double buffering. And eventually, again, you want to run a few epochs, so you shuffle the data, you retrain again. What's the advantages or disadvantages? So larger data sets cannot fit into the GPU memory because they're just bigger. Double buffering will try to keep up with the reads because it will try to do it. It's kind of like a best effort. It relies on the acceleration not being fast enough than what it will take to load into the GPU memory, which is sometimes true, sometimes not. But again, we have the same issues as before. Larger data sets preprocessing will still require reading these larger data sets to preprocess them. And massive metadata operations shuffling through billions or billions of files.
When I've done training in the past, it's been mostly, I guess it's not a lot of data, but I'm sitting there and effectively in a Python loop processing batches of data that are being read almost in real time off of direct storage or something like that. And so when you're talking about moving data into the GPU, I mean, it's done in batches to a large extent. So, I mean, I'm just trying to understand how this all plays out. You mentioned double buffering. I'm trying to think where that actually works in this space.
So eventually the GPU will compute on data that it has in its own memory, not even in its server memory, but in its own memory. So you need to load it into the GPU memory. Maybe you have more than one GPU and you're distributing it. So we'll look at that as one big memory and one big GPU. And the double buffering comes into effect where imagine that you're reading data from your storage into your GPU memory, and now you're running your training job. You finished on a batch because you don't train on all of the data. Obviously, there's a limit to what your model can even accept. So you finished the batch. Now you need to bring more data. Essentially, it's that time where you bring the data from your storage, you're pending on the storage. So the faster the storage, the less time you will wait, right? That's where your GPUs are idle. The double buffering rate, just to your question, the double buffering is a method in computer science, right? To say, hey, I'm instead of training on one big batch, I'll train on a smaller batch. And while I'm training on it, I'm copying from my storage. So essentially, I'm limiting my training, but
I understand the logic, Shimon. I'm just trying to understand how this plays out with WEKA.
I'm going to show that WEKA doesn't require it, but that's great. So let's compound the problem even some more, because let's take a look at a real-life environment. A real-life environment, containers, I promise it will take 2 minutes, and then we'll get to WEKA. A real-life environment, you're running on a server, you're running a containerized environment, you're running multiple training and pipelines, and they're not necessarily all at the same place. So maybe here, this guy is doing the training, that guy is doing inferencing, this guy is doing the pre-processing. So you can't even rely on anything really matching on the GPU memory or the CPU memory being fully dedicated to that. And so multiple jobs are running concurrently, different stages, heavier, lower in the RAM. And final slide on that and the problem, let's compound it even some more. Now you have, let's take a look at super pod-like configuration where we have hundreds or thousands of GPU servers, as we see with some of our customers, and they each are compounding that problem. So there is a real problem here. How do we solve it? How do we help it? Yada, yada, big problem. So looking at IO patterns, and I think that's what you guys asked about. this is a real S-trace from a TensorFlow over ImageNet. You see that the metadata load compared to the data load is massive. So in this case, it's only opens, but if we look at the entire pipeline, we see a lot of stats as well, a lot of lookups, obviously, because you're going through millions of files, right? So the metadata load is very important. And also, if you look at the I/O pattern, there's a lot of small files. There's this notion that in AI, you're only working on big files, which, by the way, is sometimes true. If you're using TF records and you're aggregating a lot of data into larger files, you get larger file workloads. But if you're working on some AI workloads, raw images or text, for example, you'll now work with a lot of small files. So you definitely need an environment, and I'm teasing it up for the WEKA solution. You definitely need an environment that can handle massive metadata, massive IOPS, and massive throughput. WEKA is that environment, and this is how. So looking at the WEKA environment, how do we do what we're doing? So
go back to that slide just 1 second.
Yes.
So you're saying that, God, a big proportion of the data is under 100 bytes? Is that what I'm seeing?
In this case, in ImageNet, yes.
Yeah, but I mean, the bottom chart is what?
The bottom chart is
of I/O activity?
Yes.
By block size?
Yes.
Right. So typically when you're training, right, even on an image data set, right, you're going to have a lot of labels associated with it, right? So think about, yeah, well, not quite, right? I mean, I would think about the metadata as being potentially separate from the labels, but imagine you have an object detector, right? So, you know, we're going to look at the scene, right? We've got an annotation for this is a person, that's a person, that's a person, this is a table, this is
David, there's 800,000 100 byte IOs, and there's only 40,000 100K IOs.
No. But like, if you were to look at an object detection data set, right, you're going to have many labels per image. And if you were to look at other types of vision, like say segmentation, where you're assigning an object to each pixel, right? You know, a pixel is going to be what, 32 bytes?
I think it represents a use case.
Yeah.
Go ahead.
But I'll go ahead, and how do we solve it? I think I tried to convince everybody that real AI workloads have some varying requirements. How does WEKA solve it? And let's obviously we can talk about the secret sauce now. How do we do it? So first of all, WEKA, as David mentioned, is fully software defined, or as Liran, our CEO, says, if you turn WEKA on its head and shake it, no server will fall, right? We're truly software defined. That actually means that we can run on-prem and on cloud in a very easy manner. And we do see AI in the cloud, and actually Ephraim is going to talk about that in a bit. We do support the multi-protocol environments. As Colin mentioned, all data is accessible through all protocols. So now if I'm ingesting data through multiple sensors or scopes, through S3 or SMB or NFS, as we do see customers doing, you don't need to move that data just for protocol compatibility for another storage environments. You ingested it into WEKA, and now you're working on that data in your high performance fashion. So that already by itself eliminates a lot of the time that a training job usually see. We also have the ability to expand our namespace between Flash and object stores, and even send the data around. So if we're talking about that edge to core problem at the beginning of the ingest, we're also able to send the data around. So we see customers setting up edge WEKA storage environments that are actually gathering the data from their local geos and are able to send the data to a centralized WEKA cluster where the training will be done. WEKA does the data movement, so we can manage the data movement at exabyte scale. We solve that, and to the cloud. Moving on.
So Shimon, I have a question for you. So a lot of customers collect petabytes of data, but they don't process petabytes of data at the same time. So what is WEKA doing to allow people to collect petabytes of data, but to be cost efficient and performance efficient for the data that is being processed right away?
Great. So as mentioned, WEKA has the capability. WEKA has the WEKA Flash tier, and we're going to talk about how we're doing that. And it also has the ability to virtualize the capacity between the WEKA Flash tier and object stores, one or more in the same data center or multiple data centers. So we see actually massive ingest. So I'll give an example from a real customer, a customer that has a 3 petabyte WEKA Flash tier and 100 petabyte object store. So now we're virtualizing that capacity and we're presenting that 100 petabytes. So obviously, if you look at the economics of that solution. It's the economics of a 100 petabyte object store, very cheap, and the economics of a 3 petabyte WEKA flash tier, which, by the way, when we constantly compare prices, I'm not the price guy, but when we constantly compare prices, we're very cost efficient even on that tier. So WEKA gives you that capability to aggregate all of the data, create it. WEKA is the pass-through to that virtualization of capacity, and you just work with WEKA. You don't need to try to move the data between WEKA and the object store. You just work through WEKA. Yes.
So if I understand correctly, so part of what you're saying is that, I think you had asked a question earlier about, okay, how can you like get rid of everything from tape to hot storage, right? And I think sort of your answer is right. You on the tape system, you can have a WEKA kernel module resident there, a client there, and then that will sort of abstract away while representing the performance and capacity trade-offs that you've got for, whether it's tape, an array, a pile of flash, or something in the cloud.
I would say that WEKA virtualized these different storage tiers in a way that you only communicate with WEKA. Right. And then we'll talk about how we're doing a lot of things that even when the data is here, it's accelerated while going through WEKA. But then you just work through WEKA, and then WEKA sends the data, whether it's an on-prem object store, a cloud object store, whether it's a tape library that speaks S3, by the way. We also have some use cases that are looking at that. But the entire thing is that, I think to Frederick's question, economics and performance, everything goes in. WEKA does the data mobility between that virtualized capacity. But
where's the metadata in this?
Great question. Let me say something, and then it will be apparent. What we do is, what I like to show about this slide is what you don't see here. You don't see JBODs, JBOFs, RAID controllers, UPSs, storage class memory. You don't see different protocol gateways, different NVMe fabric. You don't see them because they're not here. They're not needed. We don't need them. What we do is we actually distribute, and maybe I'll show this slide, scale out data and metadata. What we're doing, and that's a lot of the secret sauce, is we're actually scaling out the metadata across all of the storage nodes. So imagine, for example, in this environment, maybe I have 10 servers, 20 servers, maybe I have 1,000 servers, doesn't matter, sorry. What we're doing is we're running, each of these servers is running multiple CPU cores that is actually running multiple virtual metadata servers. So even in a small environment, WEKA can start as small as 6 nodes for your day one AI environments and then grow to thousands. Even on a small environment, we're actually running thousands of virtual metadata servers that are running across all of the storage nodes. So now statistically, maybe I'll move to this slide. Statistically, if you look at it, we're actually splitting the namespace into thousands of small pieces. And now each virtual metadata server is handling their own respective part of the namespace. I'll give an example. Imagine that you have 1,000 virtual metadata servers running on 10 servers on 100 CPU cores on the WEKA environment. Now, if you write 1,000 files, statistically, each of them would handle 1 file. So there is no single metadata server. There's no limited amount of metadata servers. All of the environment is providing metadata at a true scale out, and all of the environment is fully equalized. There's no one IO pattern that would hit one metadata servers while others wouldn't. Because as you access different files, you access different virtual metadata servers. Even better, even if you access a single file and you're accessing it in different block ranges, every 8 megabytes is also being handled by a different virtual metadata server. So I know this is an AI conversation, but for the HPC world, for example, end-to-one checkpointing, where you have thousands of cores checkpointing to a single file, we solve that. Because what we'll do is that these thousands of cores would not attack one metadata server or a small amount of metadata servers. It would just work with all of the CPUs, right, to provide metadata. So this is a true scale-out metadata. I would say, obviously, there's a lot behind the hood, but usually it's hard to scale out metadata because there's the east-to-west chatter, right? If I have thousands of virtual metadata servers and one of them fails, we need to be resilient so that others will continue where they stopped, right? What we're doing is we are running these thousands of virtual metadata servers. They don't have any east-to-west chatter. So you can basically scale out more and more and add more and more. And there's no east-to-west chatter that would get a diminishing result. We are actually using our own block layer as a journal location for each of them. So now if I have a server and it's running 100 virtual metadata servers and it failed, and now my remaining 10 or 100 servers needs to decide who's picking up, they will just allocate new virtual metadata servers, and each of them will go to their known location of the journal of the one that they replaced and just continue rolling it forward. So this is a true scale-out metadata.
How do you shard the metadata? And so you're saying each of these metadata servers, let's say virtual metadata services, is only controlling metadata for a certain segment of the file?
Of the namespace, yes.
Yeah. And so how do you, and it's really only 8 megabyte range of some file within that namespace.
Multiple 8 megabyte ranges, yeah.
Exactly. So
how do we do it? We have a hash ring, and it's all calculation.
the name effectively and going through that.
The name and the LBA within the file, yes. So the inode and the range, and it's a calculation. There is no table, because tables in memory means that you cannot scale. It's only calculation based. So a client that needs to communicate with a file says, hey, I need that inode. I'm doing the calculation. I know who owns it. At a high probability, that virtual metadata owns it. It goes and facilitates the IO. If not, that virtual metadata server will say, hey, that's the next one. So it will go to it. So there's no tables in memory. There's no lookups. It's a very cheap calculation to know where I need to go to. And that's how we sharded the metadata, right? And again, it's the files and even the block ranges within the files. So that's massive. And that's showing, if you look at all of our benchmarks, definitely if you talk with our customers, metadata is amazing. It's fast. Let's go back here. I said also scaling out the data, not just the metadata. And so what we do is actually, even if I'm working with one file, we never have locality of data. And that's hugely important because, and I think right to your question, how are you able to do everything? It's because networks are now not the bottleneck anymore. In the past, networks were 1 gig, 10 gig, 25 gig. Now networks are 100, 200, 400 gigs or the InfiniBand equivalent. What we're doing is even a single file, when I write a single file, let's take a 1 megabyte example, we're breaking that file into multiple 4K pieces, and we stripe and protect these 4K pieces across all of the failure domains, across all of the NVMEs. So if I have 10 servers, 10 NVMEs per server, I'll now break out a 1 megabyte and I'll write it in multiple stripes. And so we don't mirror, we don't triplicate, we actually erasure code with our own erasure coding, because erasure coding is kind of like you want to accelerate it. So we have a lot of things that we do to accelerate our own erasure coding as well. So the data is eventually striped across the environment in 4K pieces. So then if a customer says, hey, I wrote a 1 gigabyte file, and that translates to 256,000 4K pieces, we'll go and bring these, and it needs to read that 1 gigabyte file, we'll go and read all of them in parallel across all of the nodes in the environment. If now that customer says, or that client says, I need only a 4K or an 8K or a 60K out of that file, because our block size is only 4K, we will only go and bring these 4Ks. Now, if you compare it to traditional architecture, where the block sizes, as Colin mentioned, were mostly adapted to HDDs, so you had to use large block sizes. And by the way, I promise to finish in the next 2 minutes. So you had to use large block sizes. So now when if you now need to read 4K, you actually need to read a 1 meg or 128 meg. That's why traditional environments are struggling with IOPS and throughput concurrently. With WEKA, we don't, exactly because of that, because everything is in 4K. So we scale out the metadata, we scale out the data. There's a lot of smarter things that we're doing here, bypassing the kernel, doing our own thread scheduling, working in user space, which actually containerize, which actually allows us to run converged on the same GPU servers as the applications, if needed, or act as a remote dedicated environment. We even wrote our own network protocol, which appears to regular network as regular IP, but it's actually our own protocol. On top of that, eventually it all comes down. We can talk about technology and how we're doing things, and that's great. I'll be glad to elaborate more. But eventually, where's the value? The value is actually for customers running more training epochs, shortening their wall clock time. One of our famous slides from a real customer use case is a massive AI project that moved to a WEKA environment. Their training job took 2 weeks to train. After they moved to WEKA, it took 4 hours. So that's what we do, 2 weeks to 4 hours. That's the value. Obviously, it shows that they had some IO bottlenecks. Otherwise, it wouldn't have been accelerated. That's 84 times faster. And we do have, for example, we showed SpecSFS, AI benchmark, and other, this applies to other markets as well, where we accelerate the overall data.